Okay, so I suppose we'll start. So I welcome you all to this solving and live interaction session for the subject engineering mechanics. So today we'll be dealing with the problems from the topic of the contents of week 12, which is to do with 3D kinematics. So let us look at the first problem. A wheel of radius 2 meters. So we have a wheel which has a radius r equal to 2 meters, steadily rolls without slipping along a circular arc of radius r equal to 4 meters. So this r. So essentially it is moving like that. It is having a path like that and completes one full circle about the z-axis. This is the z-axis. About the z-axis as shown in 10 seconds. Okay. At some instant, point P, this is point P we have been given. This point P on the rim of the wheel lies in the xy plane as depicted. Considering the positive coordinate directions as shown, answer the following questions. So the first question is, let omega be the instantaneous angular velocity of the wheel in radians per second. So what is the x, y, and z component is what we have been asked first. So we can see that if we were to consider in the capital X, capital Y plane, let me just reduce the size. So we can see that if this were to rotate a little bit, say by an amount, infinitesimal rotation of theta, we will have the distance traveled by this point of contact. Let me consider this to be the point of contact. Let me call this C. So this point of contact essentially, we'll see that it would have moved by r theta, would have moved by capital R theta xy, which is having a axis about positive z. Now the same distance, if we consider in the, let us say in the yz plane, we can see that that same distance, let us call this distance s, that same distance would be given by r theta yz, but it will point into the plane of the paper because it will have the axis as minus x. So this is also equal to s by the kinematical relations because it rolls without slipping. It is moving along this thing without slipping. So essentially we can equate the two. So we have r capital theta xy equal to, I'll just differentiate this by putting this as a capital theta is equal to minus r theta yz. So from here r is constant. If we were to take the time derivative, it will be nothing but r theta dot xy is equal to minus r theta dot yz. So this is just to get the relation between the two angular velocities, what will come out to be. Okay, so now let us look at what this angular velocity is actually, the value. We have this thing here. Let us call this omega 1. Okay, so it says that the entire wheel completes one full circle of radius r in 10 seconds while steadily rolling. So omega 1, we can write it as, it completes one full circle, which is 2 pi radians, in a matter of 10 seconds. And this is about the positive z. So this is k cap. So this is nothing but plus pi by 5 k cap. This is omega 1. Now if you see from the relation, omega 1 is nothing but our capital theta xy dot in that plane. That is how it changes. So from here we can easily, another point to be seen is this disk also has an angular velocity like that, because it is rolling, it is not sliding. So that angular velocity can be calculated now. That angular velocity, let us call this disk's angular velocity as omega 2, say. So our omega 2, we can see that it will be when omega 1 is positive, omega 2 will be into the YZ plane, which will have a negative axis. So it will be negative minus, uh, okay, let me put it this way. Also, our omega 2 is nothing but theta YZ dot from the plane, from the geometry of the problem, if you see. So, but we have this relation. So from here, if we see, theta YZ dot is nothing but r by small r, theta, capital theta XZ, one minute, capital theta dot of XZ, which is nothing but omega 2 is minus 4 by 2 omega 1. So omega 2 is essentially minus 2 times of omega 1 is what we get. So omega 2 is minus 2 into omega 1 vector is pi by 5 k cap. But this is only the magnitude. We shouldn't include this. This will be minus, we have accounted. This will have a angular velocities axis will be along I. That is the x-axis, this axis. It will be pointing inwards. So with this, can we write the total angular velocity of the disk of the wheel? It's nothing but omega 1 plus omega 2. Omega 2 is the velocity this is having with respect to this arm. And that arm itself is having a angular velocity in the plane xy. So the total angular velocity of the wheel, disk or wheel, I'm using interchangeably. I hope that is clear. So the total angular velocity of the wheel is nothing but omega 1 plus omega 2 in the vector form. Why don't we write it in the component form? It's nothing but omega 1, which is pi by 5 k cap, omega 2, which is minus 2 pi by 5 I cap. Generally, we arrange the vectors with I, j, k. We could also do that, but anyway, the answer remains unchanged. So this is our angular velocity of the wheel at this instant. So we can report that x component is minus 2 pi by 5, y component doesn't exist, and z component we can see is minus pi by 5 wheel. So we have the angular velocity of the wheel. So far so good. Now let us look at the next question, what it says. If Vp represents the absolute instantaneous velocity of point P in meters per second, then its x, y, and z components are asked. So if you were to consider an axis like this, let us say I consider a coordinate system like that. And let me call this small x, small y, small z. I connect it to the arm. Now I can see that as it moves, I can calculate the velocity. I have its omega, the wheel's angular velocity I have. I just have to write the, let me call this point still remains O. So by relative motion analysis, we have seen this umpteen number of times that our velocity of P is nothing but velocity of O plus omega wheel cross R P with respect to O. So velocity of O is 0. Velocity of the wheel we have already calculated. It is minus 2 pi by 5 I cap plus pi by 5 k cap cross Rp with respect to O. Can we write that? We know that it will have a positive x component which will be equal to capital R and a positive y component which will be equal to small r. So it will be plus 4 I cap plus 2 j cap. So our velocity of P is, we have to do that mnemonic way, ijk. It will be minus 2 pi by 5, 0, pi by 5, and then this is 4, 2, 0. So if you were to open this out and calculate it, it will be I cap into minus 2 pi by 5 plus j cap into 4 pi by 5, 4 pi by 5 minus 0. So nothing, it is just 4 pi by 5 plus k cap into minus 4 pi by 5, and then that is 0. So our velocity of P, if we see, it is nothing but, you can just calculate this. Minus 2 pi by 5 is minus 1.256 I, and then 4 pi by 5 is plus 2.51 J, and it is nothing but minus 4 pi by 5. It is, so it is minus 2.51 K cap. So this is our velocity of P, absolute velocity of P at that instant. So this we can report here. So x component is minus 1.256. This is 2.51, and that is minus 2.51. Okay. So the next question asks us, what is the magnitude of the instantaneous angular acceleration of the wheel in radians per second square? And subsequently, when we get the instantaneous angular acceleration, which is alpha, we have to naturally go to acceleration, total acceleration of P at that instant. So let us look at this. So we have got our angular velocity of the wheel as it was, is it? Let me put it in that component form itself. Let me call that omega 1 k cap, and then I had plus omega 2 I cap, where omega 1 was actually 2 pi by 5, and then omega 2 was minus pi by 5. Okay. So alpha, angular acceleration of a wheel, is nothing but we just have to systematically take the derivatives. So it will be minus omega 1 plus omega 1 k cap dot plus omega 2 dot I cap plus omega 2 I cap dot. Okay. Now we have been told in the question that here we have been told that it is having a steady motion. So essentially our magnitudinal change don't exist. It is just having a constant magnitude. So essentially what is the component that drives to our magnitude? It is these omega 1 dot and omega 2 dot. These are the magnitudinal change. Essentially there is no change there. Now we know that the arm is rotating about k, and the wheel is connected to the arm and it is rotating about x with minus omega as its angular velocity. But if we see as the arm rotates, as this arm rotates, our small x cap changes. So unit vectors also change in 3D kinematics. So we need to account for that change in our acceleration vector. So we can see that everything rotates with an angular velocity of omega 1. So essentially our alpha wheel, if we see omega 1 into omega 1 k cap cross k, if I were to write this, derivative of a unit vector, if I see I dot will be whatever angular velocity is there crossed with I. This will be the change in, because the essentially the magnitude of the unit vector remains the same. The direction is dictated by the actual angular motion. That is why this comes out as omega 1, because the entire system, the arm O to the wheel, it rotates with omega 1 as its angular velocity, plus omega 2 I cap, I can write it as omega 1 k cap cross I cap. This I know is 0. So essentially I have alpha of the wheel as omega 1 omega 2 k cross I is j. And if I were to substitute omega 1 and omega 2, I have written them here. So if I were to just substitute that, I'll get 2 pi. Omega 1 is 2 pi by 5 into omega 2 is minus pi by 5 j cap. So my angular acceleration of the wheel, if I see, it comes out as minus 2 pi squared by 25 j cap. If I were to calculate the value, minus 2 pi squared by 25. So this is minus 0.789 j cap. Fine, 789 j cap. So one interesting thing to note here is, when we were dealing with planar problems, when we said that a disk or a wheel rolls without slipping, we did not have any angular acceleration. Why? Because in the plane of the problem, there is essentially no magnitudinal change. But when we come to 3D kinematics, the unit vectors could change, about which we are representing the angular quantities. Because of that, there will be magnitudinal change as well as directional change. It is quite possible that magnitudinal change might not exist, but still we need to account for the directional change. That is the only part that comes in as an addition. Because if we have a rotation about one axis, that axis itself can have another rotation. So that is what we need to account for. That is the only additional part here. So although our wheel and the arm that connects the wheel to our axle, it rotates, everything is rotating with a constant magnitude, constant speed, so to speak, we still have an angular acceleration for that wheel because of the directional change. So our angular acceleration for the wheel comes out as minus 0.789. So magnitude is asked. So is equal to 0.789 j cap. Okay. So the logical next step is calculating the acceleration of P. So can we write that acceleration of P is acceleration of O plus omega wheel cross omega wheel cross R P with respect to O plus alpha of the wheel cross R P with respect to O. So we know these quantities. This is 0 and this is this we got as omega of the wheel we had got here. It is this thing. This is my omega wheel k cap. This crossed with omega cross r naught. I won't write it again because I've already calculated it. This quantity, if I see, this quantity we have already calculated in the last question. It is nothing but velocity of P. So velocity of P, we have it here. This is my velocity of P, minus 1.256, 2.51, 2.51. So I can directly write it instead of doing the cross products all over again. So it is minus 1.256I plus 2.51 J minus 2.51 K cap. So we have accounted for that. And then I have alpha minus 0.789 K cap, sorry, J cap, J crossed with our RP with respect to O. RP with respect to O, we remember it was 4I plus 2J. So we just need to calculate the quantities here. Okay. So acceleration of P, let me do it in the next page. Acceleration of P comes out as, again I have to do the cross products. IJK, I have my minus 2 pi by 5, 0, pi by 5, and then I have my velocity here, minus 1.25. I hope it was 1.256, was 256. Okay. Yeah, this was 2.51, and then this is minus 2.51. And then this is J. This we can simply do. This is what we have been doing all through. Because we have only one quantity, we can distribute and multiply it. We just don't need to write the determinant essentially. So J cross J, we know that it will be 0. J cross I will only exist. So J cross I is, we can write it I, J, K. J cross I is minus K. So minus minus cancels out. So this will be 0.789 into 4 K cap. So let us expand this out. It will be I into minus 2.51 pi by 5 plus J into minus 1.256 pi by 5 minus 2.51 into 2 pi by 5. 2 pi by 5. This is my J, and then I have my K cap, which is nothing but 2.51 into minus 2 pi by 5, and then the other one goes to 0, and then I have 0.789 into 4 K cap. This is also K cap. So I can just simplify and write it out here. So it is minus 2.51 into pi by 5. It is minus 1.577I minus 1.256 into pi by 5 minus 2.51 into 2. This is minus 3.94 J cap. And then K cap will be the sum of the two. So 2.51 into minus 2 pi by 5 plus 0.789 into 4. It comes out essentially nearly 0.001. Actually speaking, if you were to do the proper cross products with long this thing, it will come out to be 0. But we can, just for completeness sake, let me write it. 001 K cap. So this is my acceleration of P, of point P. So if we can see that the K cap doesn't contribute anything to the magnitude because it is negligible actually. So what have we been asked? Here angular acceleration. Yeah, so we have been asked to report the acceleration here. We have been asked to report the absolute acceleration, which is nothing but the magnitude of this vector. So magnitude of AP, if we were to calculate, it is minus 1. Comes out to be 4.24. So our acceleration of P vector's magnitude is nothing but 4.24 meters per second squared for this problem. So this ends this problem, 4.24 meters per second square. So are there any questions in what we have discussed? If there are, please, please feel free to ask, and I'm happy to take them now. Is it clear? Naturally, it is just an extension of what we have been doing. Only difference being that we have our unit vectors changing because of the rotation in 3D. So we have to account for our directional change as well as magnitudinal change. That happens to be the only difference. Okay, so that happens to be the only difference. Other than that, our relative motion analysis that we have developed for RFR for normal translating axis, they still hold here. Only thing is we need to account for the directional change. That is all there is. So if there are any questions, please ask, or else we'll move on to the next problem. Okay, so I take it that it is clear. I just have one small problem here. You can just take a look at this. So in order to bring a glass window from position A, this is position A, to A prime, which of the following options, there could be more than one, represents the correct sequence of finite rotations of arbitrary magnitude? So we have been given whatever magnitude we want, we can choose. Only constraint is that we have to go by whatever axis that has been mentioned in the question. Of arbitrary magnitudes that need to be imparted to this window. So there could be more than one answers here. So how can we go about having that? The essence of this question is that finite rotations are not vectors, only infinitesimal rotations are vectors. So as finite rotations, magnitudes become smaller and smaller, they approach. And in the limit that it goes to infinitesimal rotations, we can decompose them into vectors and separate them out. Essentially, that is what we have done in the first problem. If you see, the wheel is having a rotation, and then the arm itself is having another rotation. So we considered the infinitesimal case where it is just having a slight rotation, and related the kinematical quantities, differentiated them, we got the angular velocity relation. That is how we have solved. Whereas that is not possible when we have finite rotations. How we can see this is because these are not commutative. That is, these depend on the sequence in which they are imparted, as we will see in this problem. Okay, so plus x. If I were to see here, plus x means that my axis of rotation should essentially be like that. It should be into the plane. That is, my thumb, when I rotate it with using the right hand rule, the sense of the rotation should be such that my thumb points in the positive x. So essentially, it has to be rotated this way. If I see, only then it will point like that in the yz plane. Okay. So in the yz plane, can I rotate it by any angle in order to get to a plane where I can then rotate it about positive z and get to this final configuration? Any clues? Let us say I rotate it by plus pi by 2 in positive x. So what happens? We have this thing comes like that. What happens is the window comes to this configuration. So this becomes my window now with 0.2 here and then 1 over there. Now, if I were to rotate it by pi in the positive z-axis, I can see that this will take a path like that and come here. This will take a path like that and come there. This will be my axis of rotation. So we can see that I can achieve this configuration by rotating pi by 2 about positive x, and then pi about positive z. So my option 1, it actually helps me to reach the final configuration from A to A prime. Okay. If we were to analyze another case, to drive home the point that these are not vectors, let us consider option C and option D, because we can see that it is nothing but commutative. It has been represented as commutative. First, we put a rotation about minus z, followed by a rotation about plus x. Then the option D is plus x first and then minus z later. So if these two give the same result and help us reach from A to A prime, that implies that these can be considered as vectors. But finite rotations are not vectors. So that is what we will see, that out of these two, only one will help us reach the final configuration. So if I rotate anything, if I rotate this window about z in the minus z direction, I'll be able to see that if I were to do it by pi, I'll have my window like that, or pi by 2 rather. So after this, no matter what rotation I provide in the x-axis, I'm able to see that the longer arm is parallel to the x-axis and it can never be perpendicular, whereas our final configuration has a longer arm perpendicular to the x-axis. So our option C can never be achieved. Option C can never help us reach the final configuration from A to A prime. Whereas if I were to just reverse it, let us say I start with rotating about x and then in a minus direction about positive x. We just saw that it is possible. Essentially, what we did in option 1 was we gave a positive pi by 2 rotation about plus x, and then we rotated by plus pi about z. We can see that if that were the case, we can easily rotate about minus z also. Even if we were to give it a rotation of minus pi about the z, we will still reach the same configuration. So our option D essentially helps us to reach that configuration from A to A prime. So if I were to rotate this first with respect to plus x and then with respect to minus z by some quantities A and B, I'm able to reach the final configuration from A to A prime. Whereas if I were to reverse this, first apply the rotation B with respect to z and then apply A, I won't be able to reach the final configuration as we saw. So essentially the point of this question is that finite rotations are not commutative. And for them to be vectors, they need to be commutative because it should be independent of the order in which they are applied. So essentially, finite rotations don't represent vectors. As our quantities of finite rotation approach infinitesimal quantities, they start behaving like vectors. In the limit, they are actually vectors, which is what we employ time and again in order to calculate our kinematical quantities. So I hope this is clear. And regarding option B, I would encourage you to think it over as to what configuration can actually help you reach, what kind of rotation you have to impart about these three specific axes in the order that they are mentioned in order to reach the final configuration. So if there are any questions, you please ask. I'm happy to take them now. Okay, so I take it that this is clear. Okay, so in that case, let us move on to the next problem here. So we have this problem saying that a crane operator observes the telescopic boom. This is the boom of the crane. He observes the telescopic boom to increase in length at a constant rate of So these being the keyword at a constant rate of 0.8 meters relative to the crane. Okay. So this point is essentially moving away from this point at a constant angle is what the crane operator is observing, while being constantly lowered at 1.2 radians per second as shown. So we are able to see here that it is being lowered about the z-axis. So let us call this omega 1. So our omega 1 vector is nothing but minus 1.2 k cap. Okay. Now it is also known that the crane rotates at 0.25 radians about the vertical. So we have this rotation. The boom first it is increasing in length, and then it is also being lowered with minus 1.2 k cap angular velocity, and the entire crane itself is rotating about the vertical with an angular velocity of 0.25. So let us call this omega 2, let us say. So omega 2 we can see it is nothing but 0.25 j cap. Okay. Then what else is given? The boom length at the instant considered is 9.5 meters. So at this instant, that distance is 9.5 meters. Considering the positive coordinate directions as shown, so x, y, and positive z have been given. So we need to report some of the values. Let us see what they are. What is the magnitude of the instantaneous angular velocity of the boom? So we are able to see here that if the crane were not moving, if only the boom was just being lowered, then our angular velocity of the boom would have been minus 1.2 k cap because it was being lowered. But the crane itself is moving, so this component also adds up. So it is nothing but plus 0. Let me write it this way: plus omega 1 plus omega 2 is my total angular velocity. So if I were to substitute here, it is minus 1.2 k cap plus 0.25 j cap. This is my total angular velocity. So I can calculate the magnitude from here. It is nothing but it comes to 1.23 radians per second. So I have my angular velocity as 1.23 radians per second magnitude. What is the magnitude of the instantaneous angular acceleration? So now that we have this, if we can systematically differentiate this, we will be able to get our actual quantities. Let me call omega 1 vector as omega 1 k cap, where omega 1 is nothing but minus 1.2. I hope this doesn't cause any confusion. Similarly, omega 2 vector we can call as omega 2 j cap with omega 2 being 0.25. Okay, so we have this. I'll just write it again for completeness. We have omega 1 k cap plus omega 2 j cap from here, whatever way. So if we systematically differentiate this dot, uh, this is nothing but my alpha, the time rate of change of the angular velocity. which is nothing but omega 1 dot k cap plus omega 1 k cap dot plus omega 2 dot j cap plus omega 2 j cap dot. Okay, so this omega 1 dot and omega 2 dot come from the magnitudinal change, and it has been given that it is being constantly lowered and the crane rotates about 0.25 and nothing about the acceleration has been given. So both are constant. So essentially these two components go to 0. This is constant. This is also constant. Now the arm OP, the arm PQ, this arm, it is connected to our crane and that itself is having a rotation. So if we were to see, essentially K cap has a change because at another point K cap will be pointing that way and then at that way because of our rotation of the crane about the vertical axis. So that directional change needs to be accounted for. So how we can account for that is alpha, it is nothing but the entire system is actually having this rotation, which is causing the directional change in our angular velocity. So if we see, it is nothing but omega 1 into omega 2 j cap cross k cap plus omega 2 into omega 2 j cap cross j cap. This goes to 0. It is the same vector. So essentially my angular acceleration is brought about by directional change. So it is nothing but omega 1, omega 2. J cross k is, we know it is, j cross k is I. So what is my omega 1 and omega 2? I can substitute from here. It is nothing but minus 1.2 into 0.25 I. So my alpha comes out to be minus 1.2 into 0.25. It is minus 0.3 I cap. If we were to consider this to be a planar problem, let us say it did not have this rotation. Let us say it did not have this rotation and we were analyzing everything in the xy plane. Then this would have been the only omega that we would be having. And we can see that its magnitude is constant. So there will be no angular acceleration. This we have seen a number of times. We have seen that in the xy plane we will be analyzing, not specific to a plane. I'm just trying to explain the point here that when we have a constant acceleration, constant angular velocity in one plane, then its angular acceleration goes to 0 because there is no magnitudinal change. Whereas it is not the case here because it is a 3D rotation, so our axis is changing. Our essentially our angular velocity was pointing like that. After some time, it will be pointing like that. Then after some other time, it will be pointing like that. So its direction is changing. That is what is causing this acceleration to be non-zero, which was not there in our case of planar problems. Okay, so we have alpha as it was minus 0.3, so it is nothing but 0.3 radians per second squared. Now it is just a matter of extrapolation. We have already seen our rotating axis. So when VREL, when we are rotating with an axis, if we are able to observe VREL, that also we need to account. If we are accounting for AREL, we need to account for that in the Coriolis acceleration. So VQ is what is asked. VQ has been asked here. So we can see that VQ is nothing but VP. P is the point where the boom connects with the crane, plus omega plus our VREL. This we know it is 0. And then we have our omega of the boom is this minus 1.2k plus 0.25j. 25j cap plus, sorry, minus 1.2k cap crossed with our RQ with respect to P. So RQ with respect to P, if we see, this is the angle in the XY plane. So it will have only X and Y components. It is nothing but 9.5. If I were to take the unit vector in this direction, call it n cap, then my n cap is nothing but cos 35 sin 35, or let me write it in component form itself so as to avoid any confusion. Cos 35i plus sin 35j plus 0k. At this instant, it is aligned, so there is no k component. So what will be my RQ with respect to P? It is nothing but length of RQ with respect to P unit vector. So it is 9.5 n cap is my R. Similarly, VREL, if we see, V relative, the person sees that point to be moving away. So essentially it is increasing. That means n cap is the direction in which it is increasing with a magnitude given to be 1.2. So our VREL is nothing but 1.2 n cap. So we know RQ with respect to P, we know VREL now. There is nothing else in the equation that we need to substitute for. So RQ with respect to P, we know it is 9.5 cos 35i plus 9.5 sin 35j. K cap is 0, so I'm not writing that. Plus VREL is 1.2 cos 35i plus 1.2 sin 35j. So we just need to get the cross product and add accordingly. So let us do that. I have I, j, k, 0, 0.25 minus 1.2, 9 cos 35, sorry, 9.5, 9.5 sin 35 and 0. Plus, we just need to add this vector. Sin 35j. So I component comes out to be 1.2 into 9. Excuse me. It comes out to be minus, so minus will cancel out, plus j cap will come out to be minus 1.2 into 9.5 cos 35. The other one will go to 0, plus my k cap will be 0, and then this will be minus 0.25 into 9.5 cos 35 plus 1.2 cos 35 I plus 1.2 sin 35 j. So my velocity of q I can calculate. Grouping all the I terms, I can take them together. Cos 35 plus 1.2 into cos 35 comes out as 10.32 I plus 35 plus 1.2 into sin 35 comes out as minus 8.65j, and then k cap is minus 0.25 into 9.5 cos 35. So this is minus 1.945 k cap. This is our velocity of Q. So 10.32 minus 8.65, and this is minus 1.945. So we solve for velocity of Q. Essentially, only the complexity, if we see, observe carefully, this is no different than what we have been doing. The only complexity being that our cross products are more cumbersome because they are filled vectors. Rather than having just single components, they are having more than one components. So essentially, every time we have to go for this determinant mnemonic. That happens to be the only complexity. Other than that, in the physics of the problem, essentially there is not much, not a big leap from 2D to 3D. But nonetheless, we have to account for the directional change, something to be remembered. Okay. Similarly, AQ, if we see, it is nothing but AP plus omega cross RQ with respect to P plus our alpha cross RQ with respect to P plus we have our Coriolis cross VREL plus AREL. Only solace is that AREL happens to be 0 here because the crane operator sees it to be moving with a constant velocity. It increases constantly. AP 0. Rest everything we can take the cross products and calculate it. So let us do that. AQ is, so this quantity we have already calculated. That is, we have calculated it here. This is that quantity. So I will not write it again. I, J, K. My omega is 0, 0.25 minus 1.2. And then I have this. Let me calculate this. 1.2 into 9.5. 9.338. And then I have my K cap is minus 0.25 into 9.35 minus. So this is my omega. This is this component. Then I have to account for alpha. Thankfully, alpha is just one this thing. That is, it has only one component. So alpha, if we see, it is minus 0.3 I. This minus 0.3 I crossed with 9.5 cos 35 I plus 9.5 sin 35 J. And then we have 2 omega cross VREL plus 2 times I J K 0 omega 2 omega cross VREL. VREL was 1.2 sin 35, sorry, cos 35 sin 35 0 plus ARL is 0. So we just need to calculate this. So let us do that. AQ is I cap. I'll just commonly take all the I caps together. So it will be 0.25 into minus 1.945 minus 1.2 into 9.338. Let me erase this. This is 1, and then we have I cross J. There is no I cap component here. 0, and then we'll have one component from here for the I cap. So let us account for that also. it will be 0 plus sine 35. So this entire thing is my I. Similarly, j cap, if we were to do it component wise, so it will be minus 1.2 into 9.338, 0. This doesn't give, and then this will give me into minus 1.2 into 0.2 cos 35. This is my j cap component. And then I can see here I cross I doesn't give me anything. I cross j gives me positive k. So I have to account for that. My positive k will be minus 0.25 into 9.338 from here. And then I have minus 0.3 into 9.5 sine 35 minus 0.25 into 2 into 1.2 cos 35. This is my k component. So I don't want to simplify it now. You can simplify it and check with the answers that I will be posting, because I want to give an essence of the next problem also. Because if we see this process of solving this more or less becomes a mathematical rather than having a deep insight into the physics of the problem. So this I will leave it here. Anyway, when I will be posting it, I will solve it threadbare, get it to the end and then post it. So let me move on to the next problem, just to give a brief of how this is to be done. And then when I will be posting the solution in the sheet, I will be posting the entire solution so that you can refer back to it whenever you want. Okay, so let us look at this problem. A motor is mounted on a stand, rotating with omega 1. So we have been given this omega 1 is, this omega 1, we have been given as 1.5 radians per second, and omega 1 dot. So this 1.5, it is not having a constant magnitude. It has an magnitudinal change also, which is given to be omega 1 dot is equal to 0.25 in the direction. So it is actually speeding up, essentially. A shaft PQ is connected to the motor, which is operating at a constant angular velocity of 60 revolutions per minute in the direction shown. So essentially what this tells us is omega 2 is 60 revolutions per minute. So one revolution is 2 pi per minute. So this we will get it as 2 pi radians per second. And this is pointing out of the along the positive axis. So omega 2 is essentially 2 pi I cap. Omega 1, if we see, omega 1 vector is nothing but 1.5 j cap. Okay, and this is constant. This is given to be operating at a constant speed. So this omega 2 does not have a magnitudinal change. That is the essence. It is known that the collar, so we have this thing, and this is rotating about OP. This is rotating like that about OP. And then OP is rotating like that in the because of the motion of this stand. So essentially everything needs to be accounted for systematically. It is known that this collar, when this is rotating relative to this collar, or rather shaft, it is having a relative motion like this. So it is slowing down. Acceleration is negative in the opposite direction to the relative velocity. So it is slowing down. So we have been asked omega, alpha, and velocity of the collar, absolute acceleration of the collar. These four quantities we have been asked. So let me just give you a brief about how we could approach this problem. And anyway, when I will be posting, I'll be posting the entire solution. Okay, so let us connect the axis here. So if we were to take an axis like that, x, y, and then z. So this first point P will have some acceleration and velocity because of its connection with OP, because of the movement of the table. Then if we consider this axis to be rotating with this shaft, then we will be able to see the relative quantities, namely VREL and AREL. So first, considering shaft PQ, omega PQ, if the table was not rotating, omega PQ would have been just omega 2. But since the table is also rotating, we need to account for that also. So it is omega 2 plus omega 1. So our omega shaft, or rather, let me call it PQ itself. Omega PQ is nothing but 2 pi I cap plus omega 1 is 1.5, 1.5 J cap. So far, so good. Now I have been given, let me also write this as omega 2I plus omega 1j, where omega 2 is 2 pi, omega 1 is 1.5. Okay, so omega pq we have. Likewise, alpha pq, if we see, we just have to systematically differentiate it, which will be nothing but omega 2 dot I plus omega 2I dot omega 1 dot j plus omega 1 j dot. Till now, whatever two problems we saw, there was no magnitudinal change. Here we have a change in magnitude also over here. So that is just the additional part that we need to account for here. So omega 2 is rotating with a constant RPM that we have been given. So it has no magnitudinal change. This we know to be, from the problem, it is given to be 0.25. So this is nothing but 0.25 J cap. It is in the same direction, the speeding up. Okay, I cap and J cap. Now we just need to see that what component is mounted on which component. We are able to see that this shaft is having a rotation because of the stand. So essentially, our Y cap remains the same, but our X cap, at this moment it is like this, at some other moment it will be like that, then in some other moment it will be like that. So it is changing in space. So that is something we need to account for. So essentially, what is the entire system is rotating with a angular velocity equal to omega 1 because of the stand. So essentially alpha pq, if we see, it is omega 2 omega 1 j cap cross I plus 0.25 j, which is nothing but this quantity, plus omega 1 into omega 1 j cap cross j. So this is 0. This is just something we need to calculate. So j cross I we know is minus k. So it is minus 1.5 into 2 pi k cap plus 0.25 j cap. So our alpha angular acceleration of that shaft is nothing but 0.25 j, and this is 3 pi, close to 10 it will come. Yeah, minus 9.42 k cap. So we have got the angular velocity and angular acceleration of the shaft. And we have been given the relative quantities. So essentially it is the same procedure we need to follow. So if we were to write the velocity of the collar, the absolute velocity of the collar will be absolute velocity of point P. Then we have our omega PQ cross R collar with respect to P plus our VREL. Now, velocity of p, we know that this motor rotates, it is having a motion like that. So we can calculate velocity of p based on the angular quantity. So our velocity of p is nothing but omega 1 cross r p with respect to o. Rest of the quantities we have. So we can calculate velocity of the collar. Similarly, acceleration of the collar, if we see, it is acceleration of p plus omega pq cross omega pq cross r collar with respect to p plus alpha pq we calculated plus r with respect to p plus we have 2 omega pq cross vrel because of the rfr plus arel. So essentially there are no quantities here that go to zero. P has an acceleration, vrel is non-zero, arel is non-zero, alpha is non-zero. So everything we need to systematically calculate separately and then add them up together towards the end. Acceleration of p, we know it will be omega 1 cross omega 1 cross rp with respect to o, and then we have omega 1 dot, because that is non-zero, it is not rotating with a constant angular speed. Omega 1 cross r p with respect to o. I'm sorry, this is o, please take note of that, not q. P with respect to o. So once we calculate this and substitute, we will be able to find the acceleration of the collar, the absolute acceleration of the collar, because of this entire motion. With the shaft rotating about the motor rotating about this thing and speeding up. So accounting for all this is how we have to calculate the absolute velocities and absolute accelerations. So if there are any questions, please, I welcome them. I'm willing to take them now. So this question anyway, fully I'll be solving and posting, because if I go on taking cross products, it will take 2 hours, and nothing much of substance I would be able to discuss, because understandably this has lot of just multiplications. That is something that is a matter of practice. I just wanted to focus on the physics of the problem. So if there are any questions in that regard, I'm willing to take them now. No, this would be the last session. Essentially, every week we are conducting one session. So the course itself is going to end by this week. The last topic being 3D kinematics. So essentially, this would be the last session. Okay, thank you. Okay, I hope it was of some substance, and I also learned a lot because of your enchanting questions. So thank you for attending, and I hope there was some value addition to the course because of this live session. Okay, okay. Very well. Thank you for the feedback. And understandably, there has been a feedback form also that has been circulated. So I encourage you to record your honest feedback. Needn't be good or bad. Just record your honest feedback so that the people who are conducting and starting this initiative, they also get a sense of whether this initiative has been taken to its logical conclusion or not. If that be, they might continue these sessions in the future also. That is the essence. Okay, so if there are any other, no other questions, then I'd like to call it a day. I thank you all for attending this session. You can ask your doubts in the discussion forum. So we'll take it from there. So thank you all.